Good morning, ladies and gentlemen. Thank you for coming this morning. This presentation will be about an alternative phantom power supply, and it's called the True Phantom. But first, let's think about what is a standard phantom. Standard phantom is a DC electric power transmitted through a microphone cable to operate microphones that contain active electronic circuitry. And the same cable is also used to transport the AC signal from the microphone to the console, so in the opposite direction. Standard phantom power looks like this. You have the 48 volts power supply, you have the two resistors, and you have the wire 2 and the wire 3 of the XLR cable. That is standard power. The majority of manufacturers of condenser microphones use the following schematic. Here you see the capsule of the microphone, you see the input FET, you see the phase shifter, this side and this side, and you see the emitters of the microphone who give their signal to this wire and to this wire to the cable. And then you see here the preamp with the phantom power, 6K8 resistors and the 48 volts, then the blocking caps, and then the input resistors of the microphone preamp. This is the normal schematic. Clearly, you see that these resistors, all four, are a load for the emitter follower here in the microphone at the other side of the cable. Nevertheless, they have their influence on the behavior of the emitter follower. The lower the load, the bigger the distortion of an emitter follower. So what happens here is that the powering is also a load. And that is the thing I would like to change. Can we do a SPICE analysis to investigate the behavior of the emitter followers and the load of 1K and 6Ka parallel, which was the case? Therefore, if we SPICE analysis, we don't need the input FET then, so it's gone. And then we have this schematic, and we should put that in a SPICE analysis schematic, and then it looks like this. Here you have the 6K8 resistor. Here you have the emitter follower. Here is this signal, the balanced signal coming in, and here it's coming out. And these are the blocking caps, and this is the input resistor of the microphone preamp. And then you measure the result of the output. Is it possible to reduce the THD with a current source? If you put a current source in your software, then it looks like this. I use a Schups microphone. They pull 2 milliampere at both wires. And then the DC of this whole schematic doesn't change anyway. Only the AC changes. Here you see the resistors. Then you have a look at the results of this SPICE analysis. Then the standard is 3 zeros and a 9.5 in distortion, And the true phantom is 3 zeros and a 5/8. So that is 4 dB less distortion. So it looks like that there is a possibility to reduce the distortion only by this theoretical analysis. Then is the question, is that also possible in the real world? Yes. With a voltage-regulated current source, it is possible. The output should be 48 volts. With this schematic, you have a voltage-controlled current source. The output of this current source is 48 volts on this output, and then you use your two phantom power resistors, and then you put that in the microphone. And then he has what he wants, only now he doesn't see, he has no load as much as with the standard, because here is a current source. This is the first current transistor, and this is the second, to make it even better and to have a higher dynamic impedance. So this will be about 2 megaohm dynamic impedance instead of actually 0 ohm of the standard phantom. This schematic works very well. You see here the reference voltage of 48. This op-amp will DC servo the current source. He gives that much current, that 48 volts will be at the output, and then every microphone gets his current, what he used to get. Then, measurements. Then Foley was so kind to do these independent measurements on this system.
Yeah, thanks, Yossel. I had the opportunity here to measure this true phantom compared to another outboard phantom power supply using the standard Schoeps design. So this was the test setup that was used. Used the Audio Precision 555 analyzer. My friends at PCB loaned me one of their 48-volt phantom preamps along with a dummy microphone. So the electrical signal would be taken from the generator directly into this dummy mic. So it's basically replacing an actual physical acoustic capsule. And then we've got the device under test with the two different types of designs of phantom powering, and then a metal box here with the DC blocking capacitors. So that box, it was to replicate the capacitance and 1K resistors that would be that the circuit normally would see in terms of a mic preamp design. So here's just a little bit more information on that. And that test box in here, that's basically to replicate this part of the circuit. In fact, the first set of measurements that were done, this was not done there, and then we realized we need to have that equivalent loading on the 48-volt mic preamp to properly characterize the performance. So this is the microphone, quote-unquote microphone, because here's this dummy microphone capsule and then the 48-volt preamp in here. And then this is the box with the small 1K resistors and these blocking capacitors. So that was the test setup, physical test setup that was used. So this is what I thought was interesting, because my career, I've been in the test and measurement world for like about 1 billion years. And it was interesting to always have the opportunity when someone makes a model to see how well does the model actually match up with measurements. And it turns out that, guess what? The model and the measurements actually do line up here. So this is what I thought was interesting, because my career, I've been in the test and measurement world for like about 1 billion years. And it was interesting to always have the opportunity when someone makes a model to see how well does the model actually match up with measurements. And it turns out that, guess what? The model and the measurements actually do line up here. So this is the difference in harmonic distortion, just focusing on harmonics, the harmonic characteristics. And I'll show some FFT plots in a moment. Sooner than that. So what we have in here is I just put in, I was the AP analyzer doing this, put in a signal from 1 millivolt out to 1 volt, and we're seeing the differences in the THD over this particular input range. Now, in this range in here, and this is very typical, for those of you that might not be familiar with this shape of an input-output curve, typically when you see something going down as the input level is getting larger, this is typically distortion, let's say that's more noise-dominated, then you hit a point where the harmonic distortion starts to increase. And that's exactly what was happening at this point in time. So now we're talking, input levels in the 50 millivolt range. And guess what? It actually is matching almost to within a tenth of a dB or better what the SPICE model was predicting. So what are some of the details here? So this is a zoomed picture of an FFT trace. And this axis might be a bit difficult to see further in the back of the room. This is dBV. So this was at an electrical output level of 150 millivolts. So the blue trace is the standard design based on that Schoeps circuit from way back when, and the red FFT trace is from the True Phantom. So if we just kind of bounce between the two, you can see that there is a difference of almost on an individual harmonic basis, almost a 5 dB difference in the second harmonic being lower. And these are 5 dB increments between the major lines and about a 7 dB difference. And then also just overall less noise if I just go between the two. So that was very, very interesting to see that change in performance. So the other aspect, too, is what about noise floor? Because especially when you're recording at quieter passages, have a sensitive microphone, and so on, and the noise floor is better. The gray curve is the test box itself. So in essence, this is our reference. What this hump in here is probably due to just some DC offset. But here we're seeing the True Phantom circuit design. So yes, everything is going to have noise, as we know, but it's also a very, very flat noise spectrum, whereas the standard circuit, at least this particular implementation of it, I don't want to necessarily say that this standard circuit for 48-volt phantom powering will always give you this noise, but this particular product that I was using as my device that utilizes the standard design was showing these sorts of noise characteristics. But even if you discount this, there is still lower noise. And this is 10 dB differences in here. So we're still talking several dB of lower noise on a bin-by-bin basis. So the noise floor in general is about 9 dB lower, but it is somewhat dependent upon where you're at in the frequency range.
Do other parameters change when you power it with the True Phantom? Yes, the gain. And the gain you can divide in effects on low frequencies and on higher frequencies. On the low frequencies, here you see that here we are very low at 10 hertz, but already here at 20 hertz, the basses are half a dB louder with the True Phantom, which is in red, as you see, and then the standard Phantom. So the roll-off is a little bit better with the True Phantom than with the standard Phantom.
And then at 1 kilohertz, very, very slight, but there's still a very nominal amount of gain. It's about a 600th of a dB. One can certainly argue is even that's audible, but from a measurement standpoint, it is there.
Here we do a comparison of sound I recorded that with my own microphones, Schupp's microphones, MK2, MK2. And I didn't change anything, of course, and I used sound of a machine. This is first is a music box, which plays every time exactly as loud as the last time. So that is good to compare. Later on, you hear the pianola. A pianola is a piano which is played by a machine with all the pressures the same, and the last is the guitar. Okay, let's listen to the effect.
Yeah, so is this, we're all set here for the audio? We'll find out.
Once more. Once more. Standard. The last one was the standard, and the true phantom was the first.
And then we'll go to the piano.
Yeah. So, to say it short, you can see it, you can hear it, and you can measure it. Does it comply to the 48 standard? Yes, it does. It gives exactly the same voltages everywhere. Every microphone works on this system as good as it did with the standard, only the load is less, and therefore the microphone works better. Okay, next. Conclusion, reduction of the THD tend to, for low tone, for low volume, 10 dB, for higher volumes, 4 dB, noise floor better bass reproduction, audio improvement of the sound quality is good to hear. It complies to the standard, and there are no disadvantages. Is it new? Yes. The patent has been granted. These are the forms. This is the standalone version. This is the chip, which is made by a German factory called Prema, and it will be available in beginning next year. And this is the barrel possibility that you put it in the console who has no true phantom yet. Yes, a little bit. The price of the chip is not yet set, but maybe he is €4 or something like that. Not that much, I think. And the number of components is neglectable. It's not big. So yes, the chip is a price.
In a regular or standard phantom power system, we have one power supply, 48 volts, and this voltage goes to every preamplifier input. So how would you treat with this current source? Would one IC, one chip, be able to supply the enough current for every input, or would I need one IC per input?
Every channel needs one IC. So as many channels you have, as many ICs you need.
Thank you.
One question about the measurements of the wideband noise floor. In your SPICE simulation, did you take into account the flicker noise in the transistors? Because that increases at low frequencies.
Have you heard it?
So that was regarding, your comment was regarding what, with the SPICE analysis or with the measurement?
Well, both actually. The fact that it goes up at low frequencies seems to me to indicate that it could be flicker noise.
It's a quick one. It's a technical question. Clearly, this technique is graphically, sonically, and everything was shown here. It shows that it improves over the standard phantom power circuit. So would you explain in few words this change, this improvement? So what this current source, how it affects the microphone in order to have this kind of improvement?
So what's the using the constant current design? What's happening with
So why it has its effect? That is because the load for the microphone is lower, and therefore there is less THD, and that is what happens. The only disadvantage is that you need a little bit more voltage than the 48. You need 60 or something, because it has to have some room to do his calculation, to this current source function. Is that what you ask?
Half.
Half.
Yeah, because with the current source, we have the current source itself has a high output impedance,
Yeah.
which becomes transparent to the circuit.
Yes.
However, the microphone input circuitry usually use a low impedances, like 2K, 1K, or something around this value. So, of course, two 6.8K resistors across the input give some load to the circuit, and a current source does not. If it has high impedance, how it should be. So, and
Yeah.
well, I understand. The fact that it's not loading the microphone allows the microphone to behave differently or freely the way it should be, perhaps. So we probably can talk later on.
Let's do that.
Thank you very much.
Let's do that.
Yeah,
Time's up.
all right, thank you very much.
Thank you.